In this video, we are going to look into organometallic reagents and hydride ion donors. Grignard reagents and organolithium reagents react with carboxylic acid derivatives to give tertiary alcohols as the final products. Typical carboxylic acid derivatives that are used in these type of reactions are methyl and ethyl esters. Because alkoxy group is lost in the course of reaction, inexpensive esters are the best starting materials. And we can here examine reaction mechanism on example of reaction of methyl cyclohexane carboxylate with methyl magnesium bromide. So first step is nucleophilic addition to the carbonyl group. So nucleophilic addition of Grignard reagent of carbon nucleophile to the carbonyl group, and the intermediate is typical tetrahedral intermediate. It is unstable. Carbon-oxygen double bond reforms. So free electron pair from oxygen flows back to reform carbon-oxygen pi bond, and that results in loss of methoxy group, leaving group. Product is corresponding ketone, in this case methyl ketone, and methyl group comes from Grignard reagent. In the next step, one more equivalent of Grignard reagent adds to ketone, because of course ketones react with Grignard reagents. So one more equivalent of methyl magnesium bromide adds, carbon nucleophile again forms bond to carbonyl carbon, and second tetrahedral intermediate forms. This tetrahedral intermediate does not have a leaving group, so this alkoxide is the final product of the Grignard reaction. Upon protonation, tertiary alcohol is isolated as the final product of this synthetic sequence. Another class of carboxylic acid derivatives that could be used in these type of reactions are acyl chlorides or acyl bromides, but they are much more expensive and much less stable compared to esters, so they are relatively seldom used. Otherwise, products are the same. So they react with two equivalents of Grignard reagent, and upon protonation, tertiary alcohol is isolated, and two substituents in tertiary alcohol are identical because they originate from the Grignard reagent. Grignard reagents react with nitriles, and upon addition of a Grignard reagent to a nitrile, the intermediate is imine salt. So carbon of nitrile, which is sp hybridized in the starting material, in imine goes to being sp2 hybridized. So carbon goes from sp to being sp2 hybridized, and then imine salt intermediate, upon treatment with water, is protonated and hydrolyzed to the corresponding ketone. So products are ketones. So result of addition of Grignard reagent to a nitrile is the corresponding ketone. Organolithium reagents react the same way. So organolithium reagents readily add to nitriles, and upon hydrolysis, ketones are isolated as the final products. Here is a summary of the use of Grignard reagents in organic synthesis. I will go relatively quickly through it. You may want to pause the video here and study this in a bit more detail. Reaction of Grignard reagent or organolithium reagent with formaldehyde upon workup gives primary alcohol, and that alcohol has one more carbon atom compared to the starting organometallic reagent. Reaction of Grignard reagent or organolithium reagent with epoxide also gives primary alcohol, but this primary alcohol has two more carbon atoms compared to the starting organometallic reagent. Reaction with an aldehyde results in formation of the corresponding secondary alcohol. Reaction with a ketone results in formation of a tertiary alcohol, and in this case, all three substituents on tertiary alcohol could be different. Reaction with an ester or an acyl chloride, so carboxylic acid derivatives, results also in formation of a tertiary alcohol, but in this case, since two substituents originate from organometallic reagent, two substituents must be identical. Reaction with carbon dioxide, upon acidic workup results in formation of the corresponding carboxylic acid, and that carboxylic acid has one more carbon atom compared to the starting organometallic reagent. Reaction with water, of course, results in protonation of the organometallic reagent, and corresponding hydrocarbon is obtained. Finally, reaction with a nitrile upon workup gives the corresponding ketone. Carboxylic acids and derivatives undergo reduction reactions with hydride ion donors. Typically, lithium aluminum hydride and various derivatives of it are used. Here is a mechanism of reduction of an ester with lithium aluminum hydride. In the first step, lithium aluminum hydride donates hydride anion to the carbonyl carbon, so hydride nucleophile adds to the carbonyl carbon of the ester, and that results in formation of a tetrahedral intermediate. Next, this tetrahedral intermediate is unstable. It has a leaving group, alkoxy group, in this case methoxy group, so carbon-oxygen double bond is reformed. Free electron pair from oxygen flows back to reform double bond to carbon, and that's accompanied by breaking of carbon-oxygen bond to methoxy group. So methoxy group leaves as a leaving group. The result is formation of aldehyde as an intermediate. Of course, aldehydes are highly reactive, even more reactive than esters, and so second reduction step readily occurs. In the second step, hydride anion adds to carbonyl carbon of the aldehyde to give the intermediate lithium alkoxide. This is where the reduction stops, and then upon acidic workup, corresponding alcohol is isolated. So from this mechanism we can see that esters and similar carboxylic acid derivatives, basically oxygen-containing carboxylic acid derivatives, are reduced to corresponding primary alcohols. Carboxylic acids and derivatives are readily reduced upon treatment with hydride reagents, with complex metal hydrides. First, just for comparison and to remind you, this is a reaction we covered earlier in previous videos. Aldehydes are reduced upon treatment with lithium aluminum hydride to corresponding primary alcohols. Esters are also reduced upon treatment with lithium aluminum hydride to corresponding primary alcohols, and as you can see from this example, carbon-carbon double bond doesn't present a problem. So carbon-carbon double bond is tolerated in reactions like these. Carboxylic acids themselves are also reduced to primary alcohols. If we wish to reduce an ester to an aldehyde, we cannot use lithium aluminum hydride. As we have seen from previous mechanism, aldehydes are the intermediates. As they are more reactive than esters, they will immediately be further reduced to alcohols. But we can use different reagent, and that reagent is shown here. It's diisobutyl aluminum hydride, or DiBAL-H. That reagent is less reactive compared to lithium aluminum hydride. It has two hindered diisobutyl groups, diisobutyl substituents, so that makes it much less reactive. And also it has only one hydride anion available for donation. So if we use the reagent in stoichiometric amount, then after the first nucleophilic addition of the hydride, there will be no more aluminum hydride left for the second reaction, for subsequent reaction. And so reaction is going to stop once aldehyde is formed. Finally, reaction is carried out at very low temperature, at minus 78 degrees Celsius, which further reduces reactivity of the reagent. Acidic workup is only needed to remove aluminum byproducts. Once aldehyde forms, there is really no need for a workup, but aluminum products would interfere with isolation of the aldehyde, and that's why we need acidic workup. This is one of the best methods to prepare aldehydes, and aldehydes are prepared cleanly and in good yields. As we have just seen, DiBAL-H reduces esters to corresponding aldehydes. It is not the only reagent used for this purpose. There are actually several reagents that we can use. Another commonly used reagent is lithium aluminum tri-tertiary butoxy hydride. And both of those reagents reduce carboxylic acid derivatives such as esters or acyl chlorides to corresponding aldehydes. Also note in this case reduction of lactone. Lactones are of course cyclic esters, so lactone is reduced by either of these two reagents to corresponding hydroxyaldehyde. Amides are nitrogen-containing carboxylic acid derivatives, and they are reduced somewhat differently. They are reduced to corresponding amines. And actually, this reaction is a very good method to prepare primary, secondary, or tertiary amine, because preparation of primary, secondary, and tertiary amides is really easy procedure, can be very easily carried out, while preparation of primary, secondary, or tertiary amines is not that easy. It's actually rather challenging. So for that reason, often we will prepare amide, primary, secondary, or tertiary amide, and then reduce it upon treatment with lithium aluminum hydride to corresponding amine. So as you can see from these examples, primary amide upon treatment with lithium aluminum hydride and aqueous workup gives primary amine. Secondary amide, again under the same conditions, treatment with lithium aluminum hydride and aqueous workup produces secondary amine. And tertiary amide upon treatment with lithium aluminum hydride and aqueous workup gives tertiary amine. Nitriles are also easily reduced upon treatment with hydride donors, and reaction with lithium aluminum hydride reduces nitrile to the primary amine, while treatment with dibal H followed by aqueous workup results in reduction of nitrile to the corresponding aldehyde. Two of the most common reagents for reduction of carbonyl compounds are sodium borohydride and lithium aluminum hydride. As we have seen in previous videos, aldehydes and ketones can be reduced by treatment with either sodium borohydride or lithium aluminum hydride. On the other hand, carboxylic acids and derivatives are reduced only by treatment with lithium aluminum hydride, and we can exploit that in synthesis to prepare desired product. For example, if we start with a ketoester shown here, reduction with lithium aluminum hydride is going to reduce both functional groups. It's going to reduce keto group to alcohol. In this case, we can see secondary alcohol on the left, and ester group to primary alcohol functionality shown on the right. So from a ketoester, product is the corresponding diol. On the other hand, sodium borohydride is chemoselective reagent. Chemoselective means that it selectively reduces some functional groups and not others. So it's chemoselective in that it reduces only keto group, but it leaves ester group intact. So from ketoester, product is a hydroxyester. And here is another example, ketonitrile. So reduction of ketonitrile with lithium aluminum hydride results in formation of hydroxyamine shown here, or amino alcohol actually, better term is amino alcohol shown here. On the other hand, sodium borohydride reduction reduces only keto group and leaves nitrile group intact. So product is hydroxynitrile. Again, chemoselectivity of sodium borohydride is shown here. We have already encountered acetals and ketals as protective groups. They also have application in chemistry of carboxylic acids and derivatives. So, for example, reduction of this ketoester with lithium aluminum hydride results in formation of the corresponding diol. And of course, we know that if we were to use sodium borohydride as chemoselective reagent, we could selectively reduce keto group and leave ester group intact. But what if we wanted to do the opposite? If we wanted to leave keto group intact and reduce only the ester group? Now we would like to reduce less reactive group and leave more reactive group intact. A way to accomplish such reduction is to first protect the more reactive keto group. So reaction of the ketoester with ethylene glycol in the presence of an acid catalyst results in formation of the corresponding ketal ester. And then reduction of ketal ester with lithium aluminum hydride reduces only ester group because ketal group cannot be reduced. Ketal group does not undergo reduction. So ester group is reduced, and acidic workup protonates the intermediate lithium alkoxide and also removes the ketal group to give the desired hydroxyketone. Here is another example, and that's selective reduction of amide functionality in presence of a keto group. So again, we protect ketone as the corresponding ketal, then carry out lithium aluminum hydride reduction of amide to the corresponding amine, and finally remove ketal group upon treatment with dilute acid. And third example involves reaction of a ketone aldehyde, where aldehydes are more reactive, but we would like to react ketone, less reactive functional group, in a Wittig reaction. So then we should protect aldehyde first, and here it's only sequence of reactions is shown, not the actual intermediates. If you wish, you can pause the video here and then work out this sequence on your own. So aldehyde is protected as corresponding acetal. So by treatment with ethylene glycol, aldehyde is converted to corresponding acetal. Then reaction with Wittig reagent converts keto group into the corresponding alkene. And finally, acidic workup deprotects acetal, removes acetal function to recover the original aldehyde function. This completes our study of reactions of carboxylic acids and derivatives with organometallic reagents and hydride ion donors. Next, we are going to look into substitutions alpha to carbonyl group.